I'm being asked a lot at the moment to go over how capacitors work, so I thought what better idea than to start the day off with a nice simple explanation of how a capacitor charges up, and we'll also look at the graph shapes that go along with it. So here's a simple circuit with a capacitor on the left there, a switch, an ammeter and a 6-volt cell. All through your school career you've been taught that if there's a break in the circuit then there's going to be no current and so nothing's going to happen. But of course, as with all things physics, that is only part of the truth. And the other thing that's important to say is that in physics all the time we deal with models, and this is a classic example of a model. Now a model isn't necessarily exactly the same as actually what's happening, but it helps us to understand. So let's consider now, first of all, what is actually going on in the cell. Well, we know that we can think of the positive plate as a whole ton of positive charges, and the negative plate similarly is a whole pile of negative charges, and you know that positive charges want to get away from each other, as do negative charges. On a capacitor, because before it's charged up, that is, the capacitor is just a piece of metal. Remember, a capacitor has two metal plates. A metal, being a metal, has a whole pile of delocalized electrons on it, but it also has a whole pile of positive charges in the nuclei. So the plate of each capacitor is actually neutral at the start. That doesn't mean it doesn't have charges on it, but it's neutral because it has an equal number of them. So let's close that switch with the black line there, and let's think about what's going to happen. Now remember, we said that this is a model and there are lots of different ways to explain how this is happening. But now we have a large area of something that is neutral over here, and a large conglomeration or a number of electrons all trying to get away from each other. Well, now you've given them a path to get away. There's a high concentration of electrons here, and zero concentration, if you like, or a lower concentration, perhaps it's better to say, on this plate. Therefore, some of these electrons now have a path to get away from each other, and so some of them will move over to the plate. Now, what drives the actual amount of electrons going is the difference in potential between the cell and the plates. Now, you can't do this, but if you imagine putting another voltmeter that could somehow just measure the voltage across the plates at the start, before anything has happened, this voltmeter is going to read 0 and the cell is reading 6. So there's a 6-volt potential difference between the cell and the capacitor, meaning that there's lots of push pushing them off onto the bottom plate of the capacitor. Therefore, at the start, quite a lot of current will flow. Now over time, the amount of negative charges on this plate build up. Now let's think about what's going on the positive plate. So going back to the start position, we have a whole pile of positive charges all trying to push each other away on the positive plate. So as soon as we close that switch, just like with the negative plate, we now have a situation where we've given those positive charges somewhere to go, to get away from each other so they can spread out over onto the top plate of the capacitor. Now again, that's not really what happens, is it? Because you know that the positive charges inside a metal don't move. It's negative charges that can flow, the delocalized electrons. So if you like, another way to think about this is to suggest that just as electrons flow onto the bottom plate, they flow off of the top plate and back round to the cell. And that's a more accurate picture really of what's going on. So for every electron that arrives on the bottom plate, one leaves the top plate and is sucked back into the cell. That means that what is happening is that the top plate is becoming more positive at the same time that the bottom plate is becoming more negative. And that means that our imaginary voltmeter in red there, instead of reading 0, now might read, say, 2 volts. This means that instead of there being a potential difference between the cell and the capacitor of 6 volts, like there was at the start, we now only have a potential difference of 2 volts. And that in turn means that there's less potential difference between the two items in the circuit pushing the current round. And so there is still current, but the current has reduced because the potential difference is less. This means that there are still negative electrons arriving on the bottom plate and negative electrons leaving the top plate, but they're not doing it so quickly. In other words, the current has dropped because, as you know, current is the rate of flow of charge. Therefore, over the next interval of time, our voltage across the plates, if you like, of the capacitor goes up to 3 volts, say. I'm just making numbers up. It went from 0 to 2, but now it's going from 2 to 3. That means, by the same argument as before, that there is less potential difference between the cell and the capacitor plate, meaning that yes, current still flows, but again, it's reduced a bit. And so we go round this cycle of electrons being pushed onto the negative plate, coming off of the top plate at a reducing rate. And that means that eventually this potential difference across the capacitor plate, notice I'm going to say approaches 6 volts, never actually quite gets to 6 volts, but is so close as to make basically no difference. And once we reach that point, then the current in the circuit effectively drops off to 0. So what would a graph of that look like? Well, what we can say is that when we first close the switch, that's the point at which the potential difference between the capacitor and the cell is at its maximum, so we'll get the most current. So we have a big value here. Now this maximum value is often known as I0, which is kind of an odd name for it really, but there we go, we're stuck with it. So what happens then is that the current falls off from its maximum value of I0 rapidly at first, see the big gradient, less rapidly as time goes on, and approaches the 0. It never of course gets there, but it approaches it. So we say it's asymptotic, or it's an asymptote, that lovely word from your maths classes. So let's just move that graph over a bit, make sure it still fits on the screen. And let's see if we can do a similar one now for the amount of voltage, or potential difference I should say, sitting on the capacitor plates. Well, at the start, before any current has flown, I think quite clearly that voltage is going to be nothing. There'll be no voltage sitting on that plate. So we start off this time down below, and we said that it's going to work its way upwards towards 6 volts, although it's never actually going to get there. So there's a line for, in this case, 6 volts, which is really known again as V0. So that means we're going to have a rapidly increasing voltage from 0 at the start. Notice the steep gradient, which is falling off and being asymptotic, or an asymptote again, to 6 volts. Then by a similar argument, let's do the graph for the amount of charge that's sitting on the capacitor plates. So just like with the voltage graph, we get it starts at 0, rises rapidly, the amount of charge on the capacitor, and moves towards a maximum value of Q0. So you can see there we have two very similar graphs. Now what's the value of Q0? Well, Q0 is the maximum charge the capacitor can take. So we know that because we are fully aware, of course, that Q on a capacitor equals CV. So the maximum charge on the capacitor then is really easy to find. You just have to use the maximum voltage times the value of the capacitor. And the maximum voltage in this case is 6 volts. There are a set of relatively straightforward formulas that control the values, as it were, on the capacitor. Although some students find these difficult to work with, and I was one of those, because of the natural logs that are going on. But once you get your head around the rules, it's relatively straightforward. So for the current graph there, what we have is just a bog standard exponential graph. The value is decreasing exponentially, so we can say that I, any time, is equal to the maximum value I0 times the exponent of some constant. And for us, that constant is 1 over RC, and then we times all that by t. So in other words, we say that the current at time t is equal to I0 times e to the minus t over RC. And for the voltage graph, now this is a 1 minus exponential graph. So we have the same exponent, t over RC, but 1 minus is being multiplied by V0 to give us V. And lastly then, in the same way, we can say that Q at time t, in other words, how much charge is on that capacitor after 2 seconds, is equal to the maximum times 1 minus e, the exponent, minus t over RC. Now, there's a lot more we could say about these formulas, and I've done a couple of questions already, which I might, if I remember, leave links to so that you can see how to use them. And Let me know if that was useful. That was a very different style of making a video for me, but we'll see how it goes.